introducing probability. And probability is kind of an easy topic in some ways, because I think a lot of the times it's intuitive, which means that even without learning the concept, you kind of have an idea about how the concept works. And sometimes the principles make sense intuitively, and maybe you wouldn't require like some kind of demonstration or proof because it just sounds right. Okay. On the other hand, there's a lot of things in probability which are counterintuitive, and things that we instinctively think are true are not. And so first we're going to start, there's a lot of paradoxes in probability, and we're going to look at one of the most famous ones today. It's called the Monty Hall problem, because there was a game show. It was popular even before I was born, so it's super old. In the game show, they had 3 curtains shown to a contestant, and the contestant was asked which curtain they chose to find their prize. And the contestant would choose one of the 3 curtains. After he chose the curtain, Monty Hall, who was the host, he would open one of the other curtains to show that behind that curtain was a goat, which is not the prize. It's like saying that the person lost. And then the person was asked, would you like to change your answer? Would you like to change your choice? And then the person decided whether they would change to the other curtain that wasn't revealed yet, or if he would stick with his own choice, okay? And then based on that, he won the car, or he didn't win the car, or he ended up choosing the second goat. All right. So people have certain intuitions about that. And it turns out that like it's not a difficult probability problem to calculate. And even though we're just in high school, it's possible for you to theoretically calculate that just with the probability that maybe you know now, or the probability that you're going to learn in the next month and a half. But ironically, even as recently as the 1970s, when that problem was published in a math journal, there was a lot of debate among professors, math professors, about which answer was correct, because the intuition was so strong and wrong that people didn't accept the answer, even though it could be proven with experiments, and it could be proven theoretically. Okay, so what we're going to do today is we're going to look at doing experiments with that. All right, I'm going to demonstrate how to use this website, and then you guys are going to go off and do a little bit on your own, testing your own intuition. Okay, so does everybody see my screen share? So I have here 2 websites. One of them is a Math Warehouse website, and the other one is Online Statbook. I think the Math Warehouse one is a little bit easier to use, so I put that one as best. If for some reason it doesn't work for you, you can try the alternate website. I'm just going to do a couple times here, and then you guys are going to do it on your own computer a few times just to get your own statistics, okay? So do you guys see the 3 doors here? They're doors instead of curtains in this one. So basically there's 3 doors, and I'm going to click on them with my mouse to show which one I'm going to choose. And then it's going to keep track of how many times I win a car or win a goat. And so like, for example, right now I'm going to say I'm going to choose the left door. So I click on the left door. So the host immediately opens one of the other doors and shows me a goat. And then it wants to know, do I want to keep my choice, or do I want to change my choice? So I say, I am going to keep my choice. So I click on my own choice, and I do win the car. And then it keeps track of how many times I win the car. So I won the car once by keeping my choice, right? To restart, I'm going to do it a few times. So I'm going to click again. So I'm gonna say, okay, now I'm gonna choose the second door. And then it shows me that there's a goat in this one. And then I say, okay, this time I'm going to change my mind. So I'm gonna click on the one that wasn't opened yet. And I won the car again. And so do you see how it's keeping track of how many times I won the car? It's also keeping track of whether I changed my choice or I kept my choice. Any questions about the scenario? Okay, and then after I do that, let's say that you go off and do this. I think you'll have time to do it 10 or 15 times. I'm gonna give you 3 or 4 minutes to do this. After you come back and you've done it 10 to 15 times, it doesn't matter if you choose to do always change your choice, always keep your choice, or do a mixture of the two because it keeps track, right? But basically, this is kind of a weird sample because I only did each one time and I won both times. But I'm gonna put my data into a spreadsheet. The place where it says record your results, today's exit ticket, and this is today's exit ticket. You're gonna go into the spreadsheet and, oh, look, JP already won once and lost once with each. I didn't put lost, I put won the goat, okay? So in my case, I won the car once by changing my choice, and I won the goat 0 times. And by keeping my choice, I won the car once, and I won the goat 0 times, right? So that's what I want you to do, but I want you to do it like 10 or 15 times. Any questions about that? Okay, you're gonna do that right now. And after you do it 10 or 15 times, you go into the spreadsheet and then fill in the number of times that each statistic happened, okay?
Mr. Tsubaki,
Yeah.
I'm clicking on the door, but the door's not opening.
Maybe try the
same.
alternate site. See if the alternate site works for you.
Okay.
Tsubaki, the same thing happened to me, and then I'm in the alternate site. But like, how do you save your data, or you just need to count how many times you do?
The alternate site? I think the alternate site keeps track also. Let me see.
It started keeping track for me, but then it kind of like cleared like at a point. After
It
I did,
cleared at a point. Let's see. There's a button that says clear data, but try again. Try again. Try again. Try again. I think it seems to be keeping track. I'm doing really bad. Look at that. It's amazing how many goats I've won. Oh, there I won one time. I won a car. Okay, no, it seems to be working. The second site also works. You just don't press clear data. Just always press try again, which is above. okay?
Okay.
But
thank
I
you.
don't think it keeps up with the amount of times we do it though. Does it?
Well, you just total it up. Do you see it says number, do you see my
Oh,
screen?
okay.
So stay trials, number correct 1, number incorrect 10. So number correct is how many times you got the car. Number incorrect is how many times you got the goat. Stay trial means how many times did you keep your choice, okay? And
Okay.
if I switch, then let's see. So I'm gonna try again. I'm gonna choose this one. Now I'm gonna switch. Yeah, it still keeps track.
How many
It even-
times should we do it?
10 or 15.
Okay.
Mr. Tsubaki,
Yeah.
this investigation probability, this doc that you shared with us,
Are you talking about the one you should print for today?
yeah,
Yeah, what about it?
are we gonna need to print it, or can I write it down on a separate piece of
No,
paper?
there's not much written on it. So this one, I think it's no problem if you just write stuff down as we go. And we're gonna start working on that immediately after we finish this spreadsheet. I made a calculation error here. Is anybody having problems doing both sides? Okay, everybody's being able to do it. Okay. We'll give you one more minute, and then like even if you didn't finish 10 or 15 times, that'll be okay. For those of you who are done, before you started this, raise your hand if your intuition told you that it doesn't make any difference whether you change your mind or not. Raise your hand, and you could raise your hand on the, raise your little blue hand in the participants box or whatever. Raise your hand if before you started this experiment, you felt it wouldn't matter if you changed your mind or not. Okay, do you guys know how to? JP raised his hand on the box. Some of you guys are raising your hand in the window, that's fine. Okay. Let's see. How you doing, Nick? Were you able to do it, Nick Toribio?
Yeah, I'm just writing down my results.
Okay, all right, as long as you were able to do it. All right, so let's take a look at the numbers that came up. You know, it's the argument that all those math professors had against the math paper that was written in the journal was that their intuition told them that it shouldn't make any difference about whether or not a goat was shown in the other curtain. That shouldn't make them change their mind. And if they did change their mind, they didn't think that it would change their winning probability, okay? But as you can see from these statistics, it's kind of overwhelming to show that changing your mind has a much higher percentage of working than not changing your mind. And we don't know anything about the probability. We didn't calculate it, but all we did was do what we call a simulation. And we can see that there's something going on here, right? And if you only did this 10 or 15 times individually, that would be one statistic that maybe could be ignored. But this would be roughly 250 trials, and we got markedly different numbers. And if we continue on and you graphed how these numbers fluctuated, you would see that they kind of converge to a number, or they approach a number the more times you do it. Okay, let's start with the lecture part. Shouldn't take too long. Let me see if I can show my phone. I'm going to stop sharing. Okay. So let me see how this is going to work. So if you have your printed out investigation sheet, you could take that out now and start taking notes. And if you don't, you could just write down, like, you know, there's not that much on the investigation sheet, just a bunch of titles, right? So you could just write the titles on a separate piece of paper and write notes there, okay? We're just going to introduce a lot of the concepts that you might have known through studying probability a little bit in the past, or just intuitively you might know. And maybe some you didn't know yet, okay? Can you guys see that very well? Do I need to put the paper closer to the camera?
It's fine.
Okay, so if you look at this, you can see that I'm first talking about outcomes. What is the definition of outcome? Outcome is basically something happening, okay? And so I put the examples from this experiment. A car appearing behind a certain curtain is something that could happen. And there's three ways that could happen. It could appear behind curtain 1, curtain 2, or curtain 3. So I put those, and I give abbreviations to them, because a lot of times in probability, we abbreviate an event as a letter or something like that. And then that allows us to use math notation to express them. So I'm going to call car between curtain 1 C1 and car between curtain 3 C3. There's also other occurrences that could happen, which is you choosing curtain 1, you choosing curtain 2, and so I'll call those CH1, CH2, CH3. Okay, so those are all like things that can happen, and we can call those outcomes in probability language. Now let's talk about sample space. So sample space is, it's like, it's a list of every possible thing that could happen, okay? And so like in this particular problem, there's kind of 9 things that could happen, which are that the car could be appear behind any one of the 3 curtains. So it would be curtain 1, curtain 2, curtain 3, C1, C2, C3. And there's 3 ways the person could choose the curtains. Choose curtain 1, choose curtain 2, choose curtain 3, CH1, CH2, CH3. But since I have 3 different ways one thing could happen, 3 different ways that the other thing can happen, if I was to make a list of the combinations of the ways that could happen, it would be C1, CH1, C1, CH2, C1, CH3, which means the car is behind curtain 1, but the person chose curtain 1, or the person chose curtain 2, or the person chose curtain 3. All those things could happen even though the car was behind curtain 1, right? And which one of those would actually be winning the car? It would be just the first one, and the other 2 would be losing, right? And I put here all 9 possibilities and made a list out of it. And that's called a sample space. When you list every single way something could happen, that is called a sample space. And it's a really useful way of calculating probability, because especially when we do problems from a high school textbook, most of the time, each outcome that you list has an equal chance of happening. So if you list 9 outcomes and each one has an equal chance of happening, then we know that the probability of one of them happening is 1/9 because we just divided 100% by the number of ways that it could happen. So that's like the most commonly used way of us figuring out probabilities. We assume that each thing has an equal chance of happening, okay? Okay, event. So event is pretty similar to outcome, and you could probably go through this class without really distinguishing between the two, and you would probably be able to get 100 on all the exams, even if you didn't distinguish between the two. Okay, they're very similar. I would say that if you're writing your IA about probability, maybe you need to be careful about the difference between outcome and event or compound event. But most of the time at this level, it doesn't really matter. Okay, basically an event is like taking outcomes, which are the simplest possible way things could happen, listed separately. An event would be putting them together. For example, if I take the sample space here, I could make an event that's the probability that I win. Okay, and if I make an event, the probability that I win, that's actually taking a whole bunch of outcomes and like grouping them together, right? Because I could win with the car behind curtain 1. I could win with the car behind curtain 2, and I could win with the car behind curtain 3. So there's actually 3 ways that that's happening. So if I say the probability that I win, I actually need to add together the probability of 3 different things to find that probability, right? So that's the difference between event and outcome. A compound event would be grouping events together. So like, for example, the probability that I win could be used to calculate the probability that I win 2 times in a row. Okay, so a compound event would be winning the first game and winning the second game. All right, if you guys have any questions, go ahead and shout out. I probably am not coordinated enough to see if you raise your hand and talk at the same time.
Should we write the examples and the definitions, or only one or the other?
This is just for you, so whichever is more meaningful for you. If you feel that the example is easier for you to remember what it is, because on the IB exams they never ask you something like define blah blah blah. They'll never say that. So it's more important for you to have like an intuitive understanding. Okay.
Thank you.
Okay, so the next one is an example of theoretical probability. Okay, so basically everything we do in this chapter is theoretical probability. Okay, which means that the textbook author has to be really careful about the problems he gives you. Okay, you guys probably haven't done too much probability since 5th grade. I think the math books that they use at EAC are pretty good about giving probability problems, but you guys stop using those everyday math textbooks in 5th grade, and then in 6th, 7th, 8th, 9th, 10th grade, probability is often something that's kind of set aside as something special if we have time or whatever, and it usually doesn't get done. Anyway, all the things that we do in school are usually theoretical probability, and there's a really fine line between a problem being easy enough to calculate for someone in high school or even in university, and a problem that is impossible to calculate. Okay, and it's just one little word in the wrong place, and the thing could be impossible for that level of student. All right, so that's kind of the challenge with, maybe let's say that you want to do an IA in probability. Okay, if you're going about it kind of backwards and you're saying, oh, I want to do an IA in probability, let me try to think of a problem that's just the right difficulty for me. If you do that, it's you're going to come up with a whole bunch of suggestions, and a lot of the suggestions will be too difficult for you to analyze. In the other direction, it gets to be too boring because like if you say, okay, let me look a list of problems that are easier enough for me to do and choose one of those, well, it turns out that that list is really famous, okay? So it's like then you end up doing something that 5 million people have done. Now, there is an alternative, which is experimental probability. So experimental probability is what we just did at the beginning of this class. Now, normally experimental probability might be done by doing a sample on a huge population, in which case the people doing all the work for you are real people doing real things. And then the other possibility is a computer running a simulation of something, which what we did was kind of a hybrid of that, right? We had a computer that had a website which allows the person to go through the scenario very quickly and by pressing buttons do it, you know, dozens of times in, you know, 10 minutes. And if you add all those trials together, then basically what you have is the same thing as a computer doing it 1,000 times, right? And for things that are kind of complicated, like calculating sports betting probabilities, one of the ways they can do it is by doing computer simulations, right? Based on the data of those sports teams playing in the past, for example. Ironically, another way that they do it is by taking the feeling of the crowd and reverse engineering that and assuming that that's like the probability that the team is going to win. If you have a lot of people betting on a certain team, a lot of times the computer is just going to take the number of people that are betting on it and assume that that's proportional to the probability that the team actually wins. And a lot of times that's correct.
Could we use that example for our IA, or would it be like too hard?
Are you talking about experimental?
Yeah, for example, like the sports.
Yeah, so, oh, well, I don't know. Just talking about that is not going to be really an IA. But we could talk about that. There might be something you could do. But, you know, probably the more interesting probability problems you can look at on the IA are not going to be theoretical. They're going to be something either where you get statistics from a crowd source, or you do some kind of simulation with a spreadsheet or with a computer program or with your calculator or something like that, and use that data. And then you kind of like do some other math process like modeling, which is, you know, fitting a curve to the result, as like the more complex math process. Okay, so like I said, it's really hard to find a perfect probability problem for your IA. But we do want it to be something that's kind of original and not just describing something that already exists. Okay. All right, so that is the difference between theoretical and experimental. And so we talked about sample spaces, and here there's a whole bunch of examples of different sample spaces. Let me take this off so it doesn't distract you. So there's how many examples here? There's 3 examples here. Oh, I forgot to do tree. I'll do tree in the corner. I have a tree. Is it covered? There it is. Okay. So here are 1, 2, 3, 4 examples of sample spaces. Remember the first sample space I showed you? It was just a list. Oops, there it is right there. That's a sample space and it's a list. I just put them out there. Hopefully in an organized way. Did you see how I tried to respect an order here? 1, 1, 1, 2, 2, 2, 3, 3, 3, and then I did 1, 1, 1, 2, 2, 2. By doing it in an organized way, when you're doing the list, you won't have any doubt when you get to the end of the list that you are at the end of the list, because that's kind of the challenge when you make a list of different outcomes, that you're like, oh, did I skip one? Is there another one? If you think back to the investigation we did for binomial expansion, where we did Doisel-Ulm, that was like the challenge, right? Whether you were wondering if you skipped one or if you repeated one. And the key is to write them down in an organized way. So the first one is grid. Grid is very similar to the list, because if you arrange the list in an organized way like I did here, do you see how it kind of imitates the placement of C1, C2, C3, and CH1, CH2, CH3 in the grid? I basically put one of the variables here, I put one of the variables across the top, and then in the middle, I just put a bunch of points to signify each one of the combinations that can happen. So like this point right here corresponds to car behind curtain number 3 and me choosing curtain number 2, right? Each one of these dots has an equal chance of happening. So since there's 9 dots, that means that each dot has a 1/9 chance of happening, okay? So grid is very useful when you have 2 variables and when each dot has an equal chance of happening, because you don't need to like represent the different probabilities in any way. You could also do more complex things, like let's say that certain combinations just don't happen for some reason. Like let's say that instead of curtain 1, curtain 2, and choosing 1, choosing 2, instead of that, it's going to be something like first contestant chooses 1, 2, or 3. And then when you choose curtain 1, the second contestant can only choose curtain 2 and curtain 3. So the grid is also useful for doing like partial grids. So you could like eliminate certain combinations because they can't be repeated or something like that. Okay, so it's really easy to see when you make a grid subsets like that. And you can check to make sure that they're correct just by the nice patterns it creates on the dots. Okay, so we're going to be doing some like that too. Table is pretty much like grid. You might say, well, what's the difference between table and grid? Table has a little bit more flexibility, because do you see how like there's open boxes at each intersection instead of a dot? So think about that. You can actually write a number in that open cell. So like, for example, let's say that the probability of the car being behind curtain 1 and you choosing curtain 3 is not 1/9. Let's say it's like 1/12 for some reason. You could write 1/12 in that box, and then you could assign a different probability for each one of these cells instead of just having 1/9 for every single one. The grid makes you use the same probability for each dot. The table allows you to change the probabilities, okay? What about tree? This is a probability tree, really useful. One of the reasons why it's useful is if you have 2 variables, it looks like a 2-layer tree where it's got 2 layers of branches. If you have 3 variables, you can't make a grid anymore. If you have 3 variables, you can't make a table anymore, because we don't have 3-dimensional paper, right? All we have is 2-dimensional paper, so we can only express 2-variable problems with grid and with table. But if we have a 3-dimensional problem with 3 variables, then we could use a tree with 3 layers. And if we had a 4-variable problem, we could make a tree with 4 layers. So the tree is very flexible. Although, you know, for a 2-layer problem, sometimes a table or a grid might be easier to visualize, okay? So do you see with the tree, what I did was I divided up the 2 things that happen into phases. And the first phase is that the car is placed behind one of the curtains. The second phase is the person chooses one of the 3 curtains. And so do you see how this maps out very easily all the possible ways it could happen? And if somebody asked you, oh, how many different ways can you win? You can visualize it pretty easily, because in the first main branch, you have one path, which is a win, which is curtain 1 and chooses 1. That would be a win. The other 2 would be losing. In the second main branch, you have one winning branch, which is curtain 2 and choosing 2, and that's a win. And the other 2 are losing. Okay, so it's really easy to visualize each possible thing that can happen. And why would you use a tree instead of maybe a grid to talk about a 2-variable scenario? Because the tree, like the table, also allows you to assign a different probability based on what happened in the beginning. Okay, so like let's say that there's a more likely chance that you choose curtain 1 because maybe you see a bulge behind the curtain that the car is making a bulge behind the curtain, and some people choose curtain 1 because of that. So maybe it's more likely to choose curtain 1 when curtain 1 has the car behind it than the others. You can actually put those different probabilities in the second layer because you can see that choose curtain 1 is in 3 different places. So if there's a different probability based on the fact that the curtain is bulging or not, then you could put those probabilities differently here, okay? And last of all, there is Venn diagram. Okay, Venn diagram is used for very specific types of problems, which are kind of like binary choices. Like this, in this problem, we have 3 choices: curtain 1, curtain 2, curtain 3. So it's kind of hard to use Venn diagram for that. And that's why I had to do some really specific scenarios here to use Venn diagram. Okay, so Venn diagram is used for 2 variables or 3 variables, and it's like kind of an opt-in, opt-out thing. Okay, last of all, I know we're coming to the end of the class. I'm going to finish in like 2 minutes, so be patient with me. So conditional probability, this is like the most difficult thing as far as people getting the right answer. But as far as understanding it, it has a really straightforward equation. So the important thing is to understand the notation and the equation and just fill in the blanks, okay? Even though it is intuitively difficult to do the calculation, it's pretty easy, okay? So how does conditional probability work? Usually when we think about probability, we don't really think about the fact that when things happen initially, it gives us more information, and then that makes the probability that the second thing happening different, okay? And here, if you look at it, we know from our experiment that changing your mind or keeping your choice actually affects the probability that you win, okay? So if I wanted to express that with the conditional probability notation, I would say the probability that you win given that you change your mind. The probability that you win given that you kept your choice, okay? And it turns out that the probability that you win given that you change your mind is equal to 1/2. The probability that you win given that you kept your choice is 1/3. So there's a big difference between winning and, I'm sorry, 2/3. The probability that you win given that you change your mind is 2/3, sorry. It's not 1/2. So it's much bigger. So the probability that you win if you change your mind is 2/3. The probability that if you win keeping your choice is 1/3. Okay. Last of all, this is a rule that we learn very early in our probability career. It's kind of intuitive, but when we actually start doing probability problems, a lot of people freak out and forget, okay? The probability of 2 things happening, if they don't depend on each other, you can find by multiplying 2 things together. So let's say the probability that you randomly pick a person at EAC is a boy is 1/2. The probability that you randomly pick a person and they're on the soccer team is 1/10. What is the probability that it's a boy and he's on the soccer team? If there's not a bias of boys playing on the soccer team more or less than girls, then you should be able to find that probability by multiplying the two probabilities together. Okay, so that's the last thing.